Hi everyone, my name is Jean Salak and I'm a PhD student at UChicago's Canon Lab. And on behalf of my co-authors from UChicago, Texas State, CSTA, and SFUSD, I'll be presenting Comprehending Code, Understanding the Relationship Between Reading, Math, and CS Learning Outcomes. And just because I'm trapped in Chicago, that doesn't mean we can't engage. You can tweet me at salad with a C with the hashtag CompCode, or you can comment on this session's listing on the Hoova app, and I will be monitoring this as this talk goes on, and I'll get to your questions as soon as I can. All right, so these are some factors linked to success in a first CS course. These include good performance in prior math and science courses, the number of programming languages you knew before taking the class, time management, and intrinsic motivation. Now, how many of those skills did you have when you were 9 or 10 years old? How many of you knew a programming language when you were 10? How many of you had good time management at 10? How many of you were motivated by anything other than rewards or punishment at 10 years old? So these are some things you can take for granted in a university CS setting for the most part, which you can't for elementary school kids, which makes teaching computing to young children really, really tricky. And with initiatives worldwide for K through 12 CS education, CS and computational thinking, or CT instruction, is becoming especially important. And at those ages, they are also learning other basic skills, such as reading and math. And while you can take those skills as a given in a university setting, you cannot assume that students have those skills coming into an elementary classroom. Which is why we need to understand how reading and math impact the learning of CS. And the main objective of this study is to figure out how reading and math can influence the learning of different computational thinking concepts and the types of comprehension displayed by students. And our hope is that by identifying the obstacles faced by students who struggle with reading and math, we can help guide the development of curricula, strategies, and teacher training that better support these students. Naturally, I'm not the only person working towards addressing this problem, so I'll highlight some prior work that my study builds upon, which focus on factors that contribute to success in CS learning. So there are studies that contribute to CS learning, but most of these are focused at the university level, and these factors broadly fall into four categories. So the first is performance in other subjects, and at the university level, math and science performance have been found to be linked to success in introductory programming. The next category is prior experience, where exposure to computers, the number of programming languages, and the existing mental models of programming have all been found to be linked to success in a CS course. The third category is student belief systems, and this include intrinsic motivation, self-efficacy, students' perception of their own understanding, and their comfort level in the course. And the fourth category is cognitive and metacognitive skills, which include problem solving, visual spatial skills, which is how well you can manipulate shapes in your head, resource management strategies such as time management, and an algorithmic articulation style. However, at the K through 12 level, these factors are relatively underexplored. So for performance in other subjects, math and English have been linked to improved CS learning. For prior experience, exposure to computers and extracurricular technology activities were linked. However, these were all done in an informal environment, and most of these studies were done with middle and high school students. Then the one study here with elementary age students was in a summer camp for high achieving students, who are definitely not representative of all students. And so we are among the few to study factors that contribute to CS learning in a formal learning environment where we have a wide range of students and for this age group. So in this study, we focus on two factors. The first is math proficiency, and the second one is reading comprehension. And we choose to focus on reading comprehension instead of broad English performance, which includes both reading and writing, because reading is a more basic skill and is a prerequisite to writing. I will next present the learning theories that help ground this work. And these are theories which explain how children learn and the content that they are learning, which contextualizes my study design. So the first set of theories I use are the neo-Piagetian theories, which improve upon Piaget's theories of how children learn. And Piaget posited that children develop based on biological maturation and interaction with the environment, and they define developmental stages that occur at particular ages. Now, Case and Fisher are the first set of the neo-Piagetian theories. So they both argue that development in children is not a straight progression through different stages and is not directly tied to age. Case argued that individual factors drive development, but Fisher argued that environmental and social factors drive development. And in this study, we focus on reading and math proficiency, which are individual factors, but acknowledge that environmental and social factors can also have an influence. Now, further improving upon Piaget's work, Comments argued that developmental changes in more complex tasks are due to prior completion of simpler tasks, not simply biological maturation. So, simpler prerequisite skills to learning programming may be reading comprehension and math proficiency, which is a link we are exploring in this study. And lastly, Halford argued that people understand problems by mapping them onto existing mental models they have, and these will differ between individuals based on their prerequisite skills, supporting the need to analyze student level factors. And now that we understand how children learn, let's introduce a framework for what they are learning. And Schultz's block model helps us understand the different types of code comprehension, and it introduces a duality between a structural understanding, which is how the code works, and a functional understanding, which is the purpose of the code. And structural understanding can be split into two components: text structure, which is syntax and semantics, and program structure, which is the data and control flow. Now, in this study, we focus on structural understanding, and we hypothesize that reading comprehension may be tied to text structure, and math proficiency may be tied to program execution. And these skills, reading and math, are skills that are developed at this age. Now that we've talked about what others have done and the frameworks that ground this research, let's talk more about what we did. So our study included 296 students from ages 9 through 10 from a fairly diverse large urban school district. And they were from one high, two mid, and one low performing school in a large urban school district. They were taught 3 computational thinking modules in Scratch, which is a block-based programming language. And at the end of each module, they were given assessments on that topic. So, as for the assessments, the evidence-centered design framework, guided assessment, design, and validation. The domain analysis part was guided by the CS K-12 framework and the K-8 learning trajectories. And the questions were designed by a team of CS and education researchers and practitioners, and then evaluated by more practitioners and a reading comprehension expert for face validity. Cronbach's alpha was also calculated for internal reliability, and in this case, questions testing the same concept should have similar results, meaning they should have high internal reliability. Now, these assessment scores were used for our data analysis. So students were split into reading and math proficiency levels. Students were either significantly below, at, or above grade level. And the ANOVA F-test was used to see if reading or math proficiency had an influence on assessment scores. And this test yields 2 values. The first one is the p-value, which is the probability that the difference observed between 2 groups was due to chance. And in this study, we used p less than 0.05 for statistical significance, which means that the chances that the results are random is 5%. The next one is the eta squared effect size, which tells us how much of the variance in a dependent variable is due to the independent variable. So for example, if an independent variable has an eta squared of 0.25, that means that 25% of a dependent variable's variance is associated with that independent variable. The type 3 sum of squares was used to account for the imbalance between the number of students in each proficiency level. And the Tukey-Kramer post hoc was used to figure out which pairwise differences were statistically significant. Now that we talk about what we did, let's talk about what we found. So we found reading to be more associated with the basic questions, while math to be more associated with the advanced questions. So on this graph, you have our y-axis here, which is the eta squared effect size, which tells us how much a dependent variable can be associated with an independent variable. And this eta squared value runs from 0 to 1, with 1 being the highest association. And while all rules of thumb are fairly arbitrary, a rule of thumb for interpreting the eta square size is that 0.01 is a small effect size, 0.06 is a medium effect size, and 0.14 is a large effect size. And on the axis, we have questions organized by difficulty. So we have E, that stands for events questions, S that stands for sequence questions, and L that stands for loops questions. So on this graph, the bars represent the reading and math, with blue for reading and red for math. And as you can see, most questions had medium to large effect sizes for both reading and math. The exception is EL2, where there was no reading effect, only a math effect. And the questions we considered basic were more concerned with the syntax and semantics of Scratch programming, while the advanced questions were more related to data and control flow. We'll take a closer look at some of these questions. I'll first start with highlighting questions where reading had a strong influence, followed by questions where math had a strong influence. So we found reading comprehension to be more strongly associated with questions that emphasize a more text surface understanding. And recall from the block model I mentioned earlier, text surface understanding is understanding the syntax and semantics of the code itself. So here are two examples of questions that emphasize a text surface understanding. First, students were shown a loop and asked to identify the number of times the loop will repeat. And this question is a text surface question because all the students really need to do to answer this question correctly is to read off the yellow block. And I'll refer to this question as the repeat iteration count question. The next question is when students are shown a loop and they're asked to identify the correct unrolled version. So this question is a text surface question for similar reasons as the first, but not only do they have to know how many times the loop will repeat, but also how the loops in the block will repeat in order to correctly unroll it. I'll refer to this question as the loop unrolling question. For the repeat iteration count question, we found that students reading below grade level to any extent underperformed. And here is a graph that compares across proficiency levels. So this shows the percentage of students who correctly identified the number of times the loop will repeat. And the gray bar on the far left shows the overall percentage. And from left to right, we have students who are significantly below, at, or above grade level in reading. And the error bars along the top indicate the variance. And the shortcut to see if there's a statistically significant difference between groups is to see how much overlap there is between the bars. And the bars don't overlap, then good chance there is a statistically significant difference between the groups. We found that students above grade level outperform students who are significantly below and below grade level, and students at grade level outperform students who are significantly below grade level. Nonetheless, students are still doing pretty well on this question. Most students, even the students who are reading significantly below grade level, could answer this question correctly. Now, contrast this question with the loop unrolling question, which is only marginally harder. The performance difference across reading proficiency levels are even more stark for loop unrolling. Almost all students who are reading above grade level were able to answer this question correctly, but the rest of the students weren't, even the students who were reading at grade level. This suggests that students were only getting a shallow understanding of loops. And the fact that students reading at grade level still struggled suggests that the challenges with loop understanding extend beyond reading comprehension, which merits further study. Now that was reading. Now let's move on and talk about math. We found math to have a stronger association with program execution questions, and these are questions that emphasize data and control flow. So I'll highlight two questions that emphasize a program execution understanding. The first question is a question where students are presented with sprites that have the same loops, but one with the loops in sequence and the other one with loops in parallel. And students are given a series of statements and asked to identify which were true about the code. And this question is a program execution question because students need to understand how the Brown event blocks along the top of these scripts control the execution. They also need to understand the sequential and parallel execution of these loops. And I'll refer to this question as the parallelism question. Now, another question is where students are shown a nested loop and we're asked how many times the crash sound will play. Essentially, we're trying to ask how many times the code in the inner loop will run. And this is a program execution question because students need to understand how control of the outer loop relates to the control of the inner loop. And nested loops were not explicitly covered in this curriculum. And I'll refer to this question as the nested loops question. Now, overall, we see that students had a lot of difficulty with parallelism. So in this question, students had to circle 2 correct statements from a set of 5. One was about the sequential code, and the other one was about the parallel code. And they were worth 2 points each for a total of 4 points, as you can see from the y-axis of this graph. And students lost 1 point for every incorrectly circled statement. So this graph, we have a box plot instead of a previous bar plot, and the box plot indicates the variance of the scores. And as you can see, students really struggled with parallelism. You can see from the gray bar that most students could only really identify one of the correct statements, if they could identify any of them. And while students who had demonstrated math proficiency at an above grade level did outperform the students who were below grade level, you can see that even their scores pretty much run the gamut, ranging from 0 to 4. And students struggling with parallelism and concurrency is a pretty well documented issue, even at the university level. But the fact that being grade level proficient at math allowed students to better answer this question, a question where students don't have to do any explicit calculations, suggests a link between the mental models built in math and needed to understand parallelism, which is a link that is worth exploring. Now for nested loops, we also see that students really struggled, likely because it was not explicitly covered in the curriculum. So in this graph, we're back to a bar graph of the percentage of students who answered the question correctly, and the error bars along the top indicate the variance. So we do see that students who are at or above grade level in math significantly outperform students who are below grade level to any extent. And an understanding of loops, especially nested loops, may be related to an understanding of multiplication. For example, multiplication can be conceptualized as repetitive addition. And if students do not have a firm grasp of multiplication, they may struggle to understand repetitive program execution. Okay, so we've seen a bunch of questions up close. Let's take a look at the whole picture. Now, what we're looking at is not an electoral map with red, blue, and purple. I know that's pretty hot right now. What we're really looking at here is a chart showing the statistical significant performance differences between the proficiency levels of reading and math. So the columns are the questions, and the rows are the pairs of proficiency levels, with the closest proficiency levels on the top and the farthest proficiency levels on the bottom. And the blue boxes are for the reading levels, and the red boxes are for the math levels, and the purple boxes are for both, if there was a statistically significant difference in both. And the farther the proficiency levels, the more performance gaps there are, culminating a gap for both reading and math in almost all questions for the furthest levels. And these gaps here underscore the need for improvement in instruction, and we should work to ensure that students who struggle with reading and math are supported when they're learning computer science. Now, these students could be supported by curricular improvements and learning strategies that scaffold the instruction of introductory computer science and computational thinking concepts. We should aim to decouple the learning of computer science and computational thinking as much as possible from reading and math skills. We can draw from fields with more K-12 research, such as reading comprehension, math education, and special education. And existing computer science strategies and tools can help. And these include Scratch Junior, which is a version of Scratch designed for younger students with more icons and pictures instead of words, and Tippency, which is our learning strategy which guides students through use-modified strategies and draws from reading comprehension strategies for students with special needs. And Tippency starts with a previewing strategy for the Scratch project and then guides students through deliberate tinkering. However, in spite of all these strategies, there's still much room for improvement, and I hope that these results spark some discussion on how we can better support these struggling students. And that wraps up my talk. If you have any questions, feel free to tweet me at Sally with a C using the hashtag Comcode, or you can comment on the session listing on the Hoover app, and I'll get to your questions as soon as I can. Thank you very much, and hope you all enjoy SIGCSE.